So last week we started on our second attempt to produce a relativistic wave equation for one particle quantum mechanics, the Dirac equation, and we're going to continue investigating this equation and see whether it's really viable as a quantum mechanics. So first, two administrative notes. So as we discussed in the first lecture, we will have a regular tutorial session on Monday, despite Carnival. If you cannot make it on Monday, then feel free to just put your questions about the exercises in the Discord channel at another time. So another thing, I've put up a document on Brightspace, a syllabus which details for each lecture which parts of the lecture notes I have covered and which you should study for the exam. Now, there are a couple of sections in the lecture notes that we will not discuss, and that will also not be exam material, but I do seriously encourage you to study these and to read them at least, because they give some nice background material. Okay, any questions about formalities? If not, let's get started. So what did we do last week? I introduced a Dirac equation, which I've copied here. So we introduced this nice slash notation for the four derivative, such that we can easily write down the equation for psi, which is this Dirac spinor, so it has four components. And what we already proved is that if we have a solution to this wave equation in my inertial system, and I transform the Dirac spinor according to the special matrix S of lambda corresponding to the particular Lorentz transformation that I'm doing to get to your inertial system, then the transformed field will automatically satisfy the Dirac equation in the other inertial system S prime. And we derived the explicit form of this matrix S of lambda. Well, actually you did in the exercises. And in order to write it down explicitly, we took our Lorentz transformation to be an exponential of a matrix, which you can get by doing many small Lorentz transformations, which together add up to a large Lorentz transformation. And then similarly, we can obtain the transformation of the spinor from composing many small transformations on your spinor. Okay, so are there any questions about this last week material? So let me already look ahead a bit at an exercise that you'll be doing on Monday. So this is a sneak preview. There we're going to look, or you're going to look at rotations by an angle alpha around some unit vector. Let's call that E. So we have some unit three-dimensional vector E. And then, okay, so we're looking at rotations in the, so it rotates vectors, say in the plane perpendicular to this by an angle alpha. So this is an example of a Lorentz transformation. So we know what happens. And what we said last time is that if we know how a field transforms under rotations, then we know something about the spin of the particles that are involved. So in particular, you're going to do this So this rotation as a Lorentz transformation lambda, it is given by one of these exponentials of a matrix omega, with omega given by the spatial components in this form. So it's linear in the angle alpha. Then there is this antisymmetric 3 tensor epsilon L. Right, and so we take all the time components, so the zeroth components, to vanish, because this rotation is not going to involve the time components of 4 vectors. Right, so they are 0. And here we're summing over L from 1 to 3. So that is our convention. Whenever we write Latin indices, it's just spatial indices. So this you will check that this really gives you a rotation of angle alpha. And then you will check that the corresponding matrix acting on spinors is given by the inner product of this vector, the unit vector E, with the spin operator, and then exponentiated, where, if you recall, the spin operator is this matrix sigma, sigma. Well, okay, you cannot recall this because we have not actually seen the explicit form of it, but this is what you're gonna show in the exercise. So this is the Dirac spin operator. And what we can see from here is that it's a 4x4 matrix, as it should, because I'm taking the exponential of it to get the 4x4 transformation of the spinors. And it's given simply in terms of the Pauli matrices in a diagonal way. Now, if you recall, the Pauli matrices multiplied by h bar over 2, they were exactly the angular momentum operators, or the spin operators, for ordinary, say for electrons in 3 dimensions, non-relativistic electrons. So what we see now is that in fact we have a pair of those. The first 2 components, they transform as if they were just a particle with an up and down spin, and also the 3rd and 4th component transform in this way. Now another thing you're going to show is then that if we look at a rotation by 2 pi, so just plugging in alpha equals to 2 pi, that you get minus the identity matrix out from this exponential. So really this is saying that if you take one of these particles, you need to rotate your system by an angle of 4 pi to return to its initial state. And this is something that, I mean, that's deeply quantum. We have no classical intuition for why this could be true. In classical physics, we're certainly used to, whenever we rotate something by 2 pi, then it should be identical to before the rotation. What does this mean for the spin of the particle? So if you recall, if you have a spin 1 particle, then I rotate it by 2 pi, like a vector. I rotate it by 2 pi, and I'm back at the original one. If I have a spin 2 particle, like a graviton, I only need to rotate it by pi in order for it to return to its original state. So what does that mean for a particle that you have to rotate by 4 pi to get to its initial state? What will the spin be? Can somebody unmute and tell me? Or just by the fact that these are the Pauli matrices that do the rotation. Where did you see this before? Spin half, very good. Spin 1/2 particles. Right, so essentially, what does the spin, the spin 1/2, spin 1, spin 2 mean? Well, it means that 2 pi divided by the spin is the angle by which you have to rotate it to bring it back to the identity. So this will be one of the exercises. So let's just take this as given. Suppose we have done this calculation. This should still be a bit, well, suspicious to you. Why suspicious? Well, I mean, what am I saying here? I'm saying I'm taking a Lorentz transformation that is a rotation by 2 pi. And I say that then the spinner, it is mapped to it minus itself. But what does that mean? Does that mean, I mean, rotation by 2 pi, that's the identity transformation, right? So what is it? Is the identity transformation going to the identity spinner transformation or minus the identity transformation? So you're saying it should be the identity matrix minus. Well, I mean, it seems like this for the spinners, but certainly, I mean, just if you look at the matrix lambda, the Lorentz transformation, well, I mean, certainly that matrix is going to be the identity matrix for a 2 pi rotation. So there is some tension here. I mean, certainly, if we do nothing, so if you look at the Lorentz transformation, that does not change your reference frame at all, then I don't want to change my spinners. Right, so there seems to be here a minus sign problem. So how is this possible? So let's think a bit about this. I mean, this is not really exam material, but I want to go through it because it's actually quite a nice argument. So how is this possible? And let's do a quick poll for this. So I've listed a couple of possibilities. So perhaps the rotations, they are of course not the most general transformations, they're part of the Lorentz transformations. So maybe we have to take also those into account. Or Does it have to do with the fact that the Lorentz group or the orthogonal group is not connected? Or does it have to do with the group not being simply connected? Or is this -1 just a phase which we should not care about anyway in quantum mechanics? Okay, so most of you have answered. So let me stop the poll and let's look at what you've answered. Okay, so the opinions are divided. That is good. Let's see. We are in a larger group, the Lorentz transformations. Well, in fact, this is not very relevant to the story because this minus sign, it already appears in a non-relativistic setting. And it remains to be well, the same issue also in the relativistic setting. The -1 is just phase. Well, it's true that it's not observable, this phase, directly, but you can imagine that you're doing an experiment where with some by some interference, part of your system is rotated by 2 pi and the other part is not, and you could get some interference patterns there that actually do affect the outcome of experiments. So actually the phase is relevant. So the other possibility that 40% of you have voted for is that the group is not simply connected. And indeed, this is the important aspect here. And I'd like to demonstrate this to you to get a bit more feeling for why it's possible to have these Dirac spinors at all. So the point is that apparently this S of lambda, the transformation for the spinors that I do, it depends not only on the Lorentz transformation lambda itself, but also how we got there. So what do I mean by that? Well, how did we get to this minus the identity here? Well, through this exponential formula. And how did we get there? Well, we got there by composing many, many small rotations or other Lorentz transformations. So what we can think of is that we look at the space of rotations. So suppose this is the space of all rotations. Or if you like Lorentz transformations, it does not matter, but let's just think of the rotations for now. So in mathematical terms, that is called SO3, or the orthogonal matrices that do these rotations. We have somewhere the identity rotation in this space. And how did we get to this rotation by 2 pi, which is still the identity transformation? Well, we composed many, many small rotations. So small rotations that add up to an angle of 2 pi to get back to the identity Lorentz transformation. Okay. But now we're saying that spinors, if you do this, they do not return to the identity, but to minus the identity. Now you can imagine that, this should not depend exactly on what very small rotations I did in order to get back to the identity. Maybe I was doing many small rotations around the x-axis, and then somewhere in between I was doing a very small rotation in a slightly different direction, and then back again. So I would be doing maybe a trajectory through the space of rotations like this. I mean, really, that should not affect how the spinners are rotated in the end, right? So you should think of the effect on the spinners as being dependent on what particular path I've chosen through my space of rotations, but it should be independent under like small deformations of this path. Now, if it were possible to deform this path to only doing a very small rotation and then a very small rotation back, meaning that I continuously deform my rotations in three-dimensional space, my trajectory there, to doing no rotation at all and ending up at the identity, then I can never have that this minus sign persists, right? Because if I really do not rotate anything, then my spinner should also not change. So the only way out here is if these deformations are not possible. So meaning that there is, if you like, some hole or some obstruction that does not allow you to deform your path of rotations to doing nothing. So this is only possible because the group of rotations is not simply connected. So remember, simply connected means that you can deform any path back to the trivial path, the constant path. And in fact, the rotation group, it admits a double cover that is simply connected. So to any rotation, you can actually associate two transformations, namely one that has a plus sign and the other that has a minus sign. And that's why we can have spinners, because there is a larger group of transformations that covers the rotation group twice that's actually acting on the spinners. Yes. Yeah, so there are two terms. There are connected and simply connected. So connected means that you can find a path from any point to any other point. Simply connected means that any closed path in a space can be deformed to a point. Right? So here I have a cartoon of it's like a torus or a donut. So there is a path that cannot be contracted within the donut. Now this is not exactly how the space of rotations looked, but it's a mental picture that might help. So there is actually a nice experimental way of verifying this, and I wanted to do this with you. So who of you has seen the Dirac belt trick before? I hope at least some of you have not, so then it's nice because we can actually have a look. Because you can actually experimentally verify that this is the case, that the group of rotations is not simply connected. And for that we look at a belt. So we have a piece of wool, we attach one side of the belt to the wool, the other side, okay, we keep it fixed at a fixed position, aligned with the end of the belt that is on the wool. And then we're asking about, well, can we maneuver this belt through space to undo certain twists or not? So here's an untwisted belt, and I can, move things around, put some twists in there, untwist it again. And then the real question is, if I have a belt that is twisted by 2 pi, can I move around this belt to undo the twist? Or if I have a belt that is twisted by an angle 4 pi, can I actually undo it? So think about it for a moment, and then let's do a poll again. Let's see, here we go. So which twists can be undone? None. Twists by angle pi, only 2 pi, or only 4 pi, or only 8 pi, and multiples of them. So you don't quite have time to go and get a belt and do this. So try to do it in your mind. Okay, I suggest we stop here. Most of you have answered. So there is a slight majority for, well, you cannot undo any twists, and then there is a couple of you that think we can only undo twists of multiples of 4 pi. So let's just see. I've got a belt here. Oh, nice belt. So the first question was, if I rotate, okay, let me see. Here you can see, if I rotate by 2 pi like this, can I undo this twist by moving around but not changing the orientation of the endpoint? So I can take it behind and here, and then, well, it's still twisted but in the other direction. If I take it behind and put it through again, well, then I have a very much twisted belt. I can play around with this, but there is no way where you can undo this twist. So how about 4 pi? So 1, 2, 3, 4 pi rotation. If now I take the pen and bring it behind like this, ooh, oh, then it's very twisted. Okay, let me go the other direction. Like this, and maybe like this. Oh, I think I've done, okay. Don't forget this one, I'll do it again. No, this is experiment. We have to do things carefully. Okay, rotate by 2 pi, 4 pi. Maybe I did 6 pi last time, I don't know. Okay. And let's see what happens. Here we go. Ah, ta-da. So the answer is yes, we can undo a twist by 4 pi, but we cannot undo a twist by 2 pi. So why is this saying that the rotation group is not simply connected? Well, really the belt resembles a path through the rotation group. So let's draw that for you. So this should be the trivial path. So why is this a trivial path through the rotation group? Let me draw just some local coordinate system at every point of my belt. Say one of the axes is aligned like transversely, one is pointing out from the red side and the other one is pointing along the belt up to here like this, all the way up to the endpoint. So since the orientations of the endpoints are the same, and no, the mapping from the endpoint to each point along the belt, it's a rotation, if you like. if I forget about the translation happening. So I got a continuous path from the identity to the identity rotation. So if I deform this belt, then I still have a continuous path within the rotation. So now actually some non-trivial rotation happens here. But it's still a continuous path. And the same is true for the twisted belt. Every time I have a continuous path, so here I will have, let's see how to draw this, one that is pointing to the back. But in the end, this coordinate system will be the same as a starting point. So this is again a continuous path through the group of rotations from the identity to the identity. And the same for the 4-pi twist. So if I look at a configuration on the belt and I just deform the belt, moving it around while keeping the endpoint fixed, that is really just a continuous transformation of paths in the group of rotations. And we've just seen, I've demonstrated for you that if I have a 4-pi twist, I can move the belt around to bring it back to the untwisted configuration. But it's not possible starting from the 2-pi twist. So this really demonstrates that the 2-pi twist path in the group of rotations is not contractible to the identity, the constant identity path. So what the spinners do is they make use of this fact by associating a minus sign to the 2-pi twist. Then the 4-pi twist will of course get a plus sign. It also shows that you cannot have particles of spin smaller than 1/2, say 1/3 or 1/4, because then it would mean that I could twist by 6-pi or 8-pi. But if I twist by 6-pi or 8-pi, I can always undo a couple of these twists using this trick. So there is always a smaller twists that bring you back to the identity. Okay, that was a short intermezzo. Of why these spinners are quite special. Now, if you know something more about Lie groups, or you will get to know in your masters, then you can understand this as a more mathematical level. Let's look at the plane wave solutions to see what these components of the spinners really represent. Now we already know something about the plane wave solutions because we have set up the Dirac equation in such a way that the components of the Dirac spinners are automatically solutions to the Klein-Gordon equation. So we expect that if there are plane wave solutions, then they should be of the form of the plane wave solutions of the Klein-Gordon equation. But that does not tell us yet how the different components should be related to each other in the actual plane wave solutions. So this is what we're going to figure out now. So what is one way to characterize a plane wave solution? Well, that is the fact that they are simultaneous eigenstates of the Hamiltonian and also of the momentum operator. in the sense that, okay, I mean, these are the operators combined into a 4-vector. So they are solutions to this eigenvalue equation. Why does this make sense that they are simultaneous eigenstates? Well, because the Hamiltonian and the momentum operators commute with each other. So we can really find such joint eigenstates. And clearly the solution of this equation is that psi of p is, well, some exponential minus I p dot x over h bar, where remember this dot is the scalar product, the relativistic scalar product. But we need a 4-vector, right? This is a spinor. So we have to put some vector in front. And that may depend on the actual momentum that we have chosen. Now this satisfies the Dirac equation if, well, let's see. So what was the Dirac equation? So we wanted IH bar d slash minus MC acting on this wave function at 0. So the d slash, so that is a derivative with respect to x and then contracted with the gamma matrices. So it brings down this momentum 4-vector. So this is p slash minus mc up e to the minus I p dot x for h bar. Okay, so what does it mean for to require this to vanish? So recall this is the p mu contracted with the gamma matrices. So this is a non-trivial 4x4 matrix. And I'm subtracting minus mc times, well, the identity matrix. I might have included it here explicitly. Acting on a vector u has to vanish. So that is just saying that u has to be an eigenvector of this matrix p slash. So asking that this is 0, it's an eigenvalue equation for u. Now, since we know these matrices explicitly, this should be relatively straightforward to find out how I should choose these vectors u. And let's look first at the simplest situation where I take the spatial momentum to be equal to 0. So now what is p slash? P slash, okay, so it's p mu gamma mu. But only the zeroth component of p is non-zero, and it's given by the energy normalized by the speed of light times gamma 0. And if you recall what this gamma 0 matrix is, it has 1, 1, minus 1, minus 1 on the diagonal. So u has to be an eigenvector of this matrix with eigenvalue equal to mc. So we can directly read off what the possible values for the energy are. So the solutions so either the energy is equal to mc squared, and then I can take u to be, well, to have either the top or the second coordinate be non-zero. So if u of 0 is a linear combination of, let's denote kind of the basis by this index at the top. So if it's a linear combination of this one or this one. If I want to get the remaining solutions, then okay, I should take U to have non-zero components for the third and fourth entry. But then in order for it to be an eigenvector with eigenvalue mc, I have to take E to be minus mc squared. So those will be linear combinations of the third and fourth entry. This. So we see that at zero spatial momentum, we have the usual rest mass energy solutions, but we also have the negative rest mass solutions. So how about non-zero momentum? So we want to solve now P slash minus MC equals to 0. And we can use a simple trick for this, namely that if I take this matrix P slash minus MC and I multiply it by the matrix P slash plus MC, then, well, you know what the outcome will be because you've looked at what is the P slash times a P slash in the exercises. So we get a P slash squared minus M squared C squared, but P slash squared, that was just P squared times the identity matrix. So if your form momentum satisfies the correct dispersion relation, as we're assuming, then this vanishes identically, this matrix. So in order to get a solution to P slash minus MC times a vector equal to 0, I can just take my vector to be P slash plus MC acting on an arbitrary other vector, and it will automatically be a solution. So in particular, I can take it acting on these 4 solutions that I found for 0 momentum to get a nice basis of the solutions for non-zero momentum. So we find 4 solutions again. Let's denote them by the index R, which runs from 1 to 4. They're given by acting with this matrix on the 0 momentum polarizations, if you like. And okay, you may want to normalize these polarizations by some real number n. But the choice of n does not affect the energy of these states. We can read off now exactly what these energies are. We just get the standard dispersion relation for the first two, but we get the opposite sign dispersion relation for the second two. Okay, so at fixed spatial momentum, we've now found 4 solutions. So after the break, we'll see how to interpret these 4 different solutions a bit better. Okay, are there any questions here? If not, let's continue at 4:30. So did anyone manage to find a belt during the break to check whether I did not cheat? Okay. So we have these 4 components, these 4 solutions. So how can we interpret these? So here's another peek preview of the exercise session on Monday. So we saw that we have the spatial momentum and the Hamiltonian commuting, so we can simultaneously diagonalize these operators, but there is actually another operator that one can, that commutes with both the Hamiltonian and the momentum, and this is the Helicity operator. So what is the Helicity operator? Well, by definition, it is the inner product of the spin operator in the direction of the momentum. So here E of P, it's the unit vector pointing in the direction of P. So let me write this Helicity. So this is the spin in direction of motion. And it takes 2 eigenvalues plus and minus h bar over 2. So now it should be kind of clear how to distinguish these 4 different solutions, or the 4 degrees of freedom we have for each momentum p. So the 4 components at fixed spatial momentum p, they correspond to having positive energy, negative energy, positive helicity, and negative helicity. So drawing this in the energy diagram that we've seen before for the Klein-Gordon equation, we have energies that can be positive, so mc squared or larger, negative, at least minus mc squared or smaller. And for a fixed momentum, you therefore have essentially 2 states, 2 helicity states, one in which the spin is aligned with the motion and the other one where it's anti-aligned. So for a particular momentum p, and for that same momentum p, you also have the negative energy states with positive and negative helicity. So these are really the 4 components that are contributing. Okay. But as you can see, we're still in the slightly inconvenient situation as we were in the case of the Klein-Gordon equation. So we still have these negative energies. As in the Klein-Gordon. So now it's not due to us kind of squaring the the dispersion relation and getting this minus sign ambiguity, now it really comes from this first order equation, but having multiple components that can have solutions for the energy of both signs. But what is the difference? Or why are we in a slightly better situation now? So let's do a quick poll. So why are the negative energies not as bad as in the case of Klein-Gordon? Is it because we have these multiple helicity states? Is it because we now have Pauli exclusion, or is it because the wave equation is first order? Okay, so let's see. Okay, opinions are divided, but nobody seems to agree with me. So why do I think Pauli exclusion is actually nice here? So what are these particles? So before we had a Klein-Gordon equation, we determined that these are spin zero particles. So what is the quantum statistics there? Do you remember the relation between spin and quantum statistic? Yeah, so there we said the Klein-Gordon describes particles that are bosons, and well, they really like to sit in the lowest energy eigenstate altogether, preferably, to condensate there. But now we have spin 1/2 particles, so they're not bosons, they're fermions, right? So what can save a fermion from, well, dropping down to negative infinite energy states? Or how come in a metal, if you think back to the first half of this course, how come in a metal, if you well, throw some current through these electrons that you're putting through the metal, do not just plummet into the different atoms, that the positively charged atoms? Exactly. So in metals we have a Fermi sea. So all the states below a certain energy, they're occupied. So Pauli exclusion tells you that any additional particles can't go there. So this is a way out that we could envision also happening in this case. So the difference is that particles are now fermions. And what was Dirac's vision here, or Dirac's proposal? Let's just block all negative energy states. So suppose all negative energy states are occupied. So this proposal is called the Dirac Sea. In analogy with the Fermi sea in a metal. So what we're doing is we're saying perhaps all these states are taken, and then any additional particle that you add can only appear with positive energy. So rephrasing this in the terminology that you have encountered in the first part of the course, we're viewing the vacuum that we see not as the real vacuum of the Dirac equation, which would correspond to having no particles anywhere, also not at negative energy states. Instead, we view our vacuum as a quasi-vacuum state. Meaning that excitations that we're having are excitations on top of this Dirac Sea. But there is one consequence of this that you've also seen before, and that is that if you're looking at this quasi-vacuum state, there are some new excitations that you would not expect in if this were just an ordinary vacuum. And that is that we can have particle hole excitations. So meaning that if all these states are occupied, then sometime it can happen. For instance, if you put some thermal energy in the system, that one of these particles here, it jumps to a positive energy state. Right? So how did Dirac interpret this? Well, he figured these holes, which are excitations on top of this quasi-vacuum, well, perhaps they are other particles that we're actually observing. So perhaps this hole here, it actually corresponds to a different species of particles. So let's figure out what are the properties of these different species of particles that are actually holes in the Dirac Sea. So suppose that this was a particle with some charge q, some mass m, say the hole corresponded to some momentum p, and some negative energy E. So what does that mean for the corresponding quasi-particle? Let's do a quick poll here. So what are the energy, momentum, charge, and mass that we would associate to this quasi-particle? If it actually corresponds to a hole within these negative energy states, corresponding to a particle with charge q, mass m, negative energy E, and some momentum p. So let's see. Okay, so the last option dropped off the screen. There was another 20% for minus signs in front of all these quantities. So let's see what we should expect. Well, so the energy and momentum, they're really additive quantities, right? So if I'm looking at the energy and momentum of the system as a whole, then if I produce a hole, that means I'm taking a particle away with these quantum numbers. So if I'm taking a particle away with a negative energy, then it will have a positive energy. So we certainly, since the energy was negative, we're now adding a minus E energy particle. So certainly, yes, and this is also corresponds to the fact that we're looking at quasi-particles with a better interpretation, positive energy interpretation. So the same is true for the momentum. We need a minus sign in front of this. Also, the charge is an additive quantity. So if we remove a particle with charge q, then that is the same as adding a particle with charge minus q. And then the mass, well, how do we read off the mass? Well, we simply look at the dispersion relation. Now, the dispersion relation for minus p and minus energy E, it will still be satisfied for the same mass m. Now, to be fair here, the mass only appears in the dispersion relation with a square, so we can't really see it there. But there's certainly nothing stopping us from taking this mass to be positive as well. Okay, so the correct option, which would also got the majority vote, is that the energy, the momentum, and the charge are flipped, and the mass remains the same. Now Dirac had, sorry? You're saying, why don't we use the same argument for the mass and say we look at the total mass of this whole system? Since we're taking a particle away, shouldn't the total mass decrease? And then, um, mhm. Yeah. So okay. So the point here is that one would only be able to actually experimentally look at such a situation through the gravitational field, I think. And then one runs into different problems. No, so the point really is here that the quantum numbers of energy and momentum, they are in total agreement with this being a particle of positive mass. So that explains this choice. Later we'll get a proper justification of this fact. Yeah, no, really. I mean, actually, you're perfectly right here. This is a bit of a problem for the Dirac Sea. As we will see, the Dirac Sea, it's a nice way of phrasing things if you're just looking at individual particles. But there are considerable problems. And one of the problems is that, okay, if you have a Dirac Sea here, I mean, there are infinite negative energy states, so an infinite number of particles should be there, which are also infinitely massive, and they should all interact via the gravitational force, but also through electromagnetic interaction. So you can imagine that actually this Dirac Sea is a very unstable situation. But as far as a single particle is concerned, it works very well, just like it does for an electron in a Fermi sea in a metal. So it still had some merit, this, but we'll see that it's actually untenable when we're looking at multi-particle systems. I guess that is the best explanation I can give. Yes, so let me write this just down. So a hole in the Dirac Sea okay, with momentum P, energy E negative, Q mass M, it really corresponds to a quasi-particle with the opposite momentum, the opposite energy, opposite charge, and the same mass. Now, at the time that Dirac was looking at these electrons, he thought, do we know of any particles that have positive charge, because the electrons have negative charge? And at the time, they only knew one of them. That was the proton. So Dirac said, this must be the proton. But then, okay, we just said that the mass should be the same, and actually the proton is like a factor 1,000 heavier than the electron. So he tried to figure out, okay, are there any ways to actually make these quasi-particles heavier by some mechanism to still be the proton? But then very soon after, within a year or two, they discovered the positron. So actually, this predicted the discovery of the positron, which is the anti-electron. So it has a positive charge and the same mass as the electron. So what we'll see later when we are going to do this a bit more properly is that really these negative energy states, they are reflecting the fact that there is an antiparticle present in the system, and this is the positron. Yes. No. So see what I'm saying here. So if I have a Dirac Sea, I mean all these states are occupied, I can take a particle away from there and by exciting it, by putting some energy in the system, and create an electron, say if we're talking about electrons. But then we're also creating a hole. And we're saying then the hole, we should interpret it as an anti-electron. So really this particle hole excitation is not producing or turning one particle into another particle. It is creating two particles at once, one electron, one anti-electron. And if they meet again, they can annihilate, which in the Dirac Sea is just thinking of this particle falling back into the hole where it came from. Now, as we already encountered, there are some pretty serious issues with this Dirac Sea. Or with the Dirac equation describing this system directly. If you remember from the metals, as far as the thermal conductivity and one particle trajectories are concerned, you don't really feel all these particles that are living deep down in the potential wells around the atoms. But there are some respects in which you do feel all the particles in the Fermi sea. And this is, for instance, that they have a very large pressure. And they also have a very large mass, as we just touched upon, as in Fermi sea. So we should be able to actually feel all these particles by some interaction, all these an infinite number of particles in this Dirac sea. And the other thing is that we're talking about particle hole pair creation, but as we're saying, that is producing two particles. But we were describing a one particle wave equation. One particle wave equation can never describe two particles. So in order to make sense of the system anyway, we need a multi-particle formulation, like the ones that you have been looking at in the first half of the course. So particle whole pair creation so it requires many particle quantum mechanics. So what is the proper description there? And we'll find out in well, soon enough. And I mean, just the fact that we need infinite particles here there are just some issues. They all have in the electron case a negative charge, so they should all interact with each other, repel each other. But there are not only issues, there are also successes. So this is what I want to focus on now. The success story of Dirac's description of electrons. And for this, we're really going to look at the non-relativistic limit of charged particles. And in particular, charged particles in an electromagnetic field. So let's fix the stage a bit. So we have a charge Q particle, spin 1/2, and at the time of Dirac, it was known that such particles, they feel the magnetic field around them. And how do they feel it? Well, through their intrinsic magnetic dipole moment. So it has an intrinsic magnetic dipole moment denoted by M. So let's write the operator for this. So it's a vector operator, and in what sense does it feel the magnetic field? Well, the Hamiltonian associated to the interaction between this magnetic dipole moment and the electric field is of this form. So it's the inner product with the magnetic field. So it is saying that the spin, it likes to align with the magnetic field. So this magnetic dipole moment, it should be proportional to its spin. So the spin matrix S, and then one can put the charge and the mass in front to get the right units. And it can be another dimensionless quantity G there. So plugging in the spin matrix for a spin 1/2 particle, so that's just the Pauli matrix. This is QH bar over 4M Pauli matrix. So this was known, and people were measuring this dimensionless factor sitting in front. So experiments, they show that this factor, which is with little imagination called the G factor, it takes values very close to 2. Very close, but not quite. So why would it be equal to 2? We'll see that this is actually a consequence of the Dirac equation. And there is no way to to really understand why it's equal to 2, or at least very close to 2, without taking into account the relativistic properties of this particle. So we'll see how that works. So in order to do this, we'll have to couple the Dirac equation to the electromagnetic field. And then once we've done this, we'll take a non-relativistic limit and see whether we can identify a term like this in the equation, in the Schrödinger equation that you get in this limit. So we're going to couple Dirac equation to the electromagnetic field. So let's denote the electric field by E. So we use a curly E to have no confusion with the energy. The magnetic field curly B. And it will be convenient to express them in terms of the scalar potential and the vector potential. Now next week we'll go into more details about the electromagnetic field and the Maxwell equations. For now we're just going to look at a static electromagnetic field and see what its effect on the particle is. So just for now, if you don't quite remember the usage of the scalar potential and the vector potential, just bear with me until next week. So they are expressed in terms of scalar potential phi and the vector potential A. It also depends on space and time through the electric field being minus the gradient of the scalar potential minus the time derivative of the vector potential. And the magnetic field is the rotation or the curl of the vector potential. Now you can imagine by just looking at these equations that it's actually convenient to group those into a 4-vector. So there is a corresponding electromagnetic 4 potential a mu, which takes as its 0th component the scalar potential, and as a spatial components just the vector potential. And we divide again by the speed of light to get the same units for both. Okay, so what is an easy way to incorporate the electric and magnetic forces that act on the particle that we're describing by the Dirac equation? Well, there is a nice trick for this, which essentially follows a minimal substitution. So the interaction of the particle with the electromagnetic field can be done via minimal substitution. So what does that mean? We take the Hamiltonian and we replace it by the Hamiltonian minus the charge of the particle times the scalar potential. And similarly, we replace the momentum or momentum operator by the momentum operator shifted by Q times the vector potential. Or in covariant notation, we're taking the covariant momentum and we replace it by, okay, maybe I want to do the contravariant one since I'm also writing the mu upstairs there, like this, shifted by the 4 potential. So actually there will be an exercise, not on Monday, but the week after, in which you're going to show that this simple shift really accounts for the correct Lorentz forces on the particle. So from here, it's really easy to find what the Dirac equation is inside of a magnetic field, because we had the ordinary Dirac equation like this, but we now simply have to shift the P mu. So that is really, I mean, this is really P slash here, P slash hat, if you like, by A. So we get this equation. So this is the Dirac equation in an electromagnetic field. Now, in order to find the interaction of the spin of the particle with the magnetic field, there is no need to look at fully dynamical electromagnetic fields. So we can safely assume that the electromagnetic field is static. So this means that phi scalar potential only depends on position and the vector potential as well. Now that is useful if we want to find the solutions to the corresponding Schrödinger equation. So let's write this Dirac equation back in the non-covariant form. So recall then instead of the gamma matrices, we had these alpha and beta matrices. So then the Hamiltonian looks like this. Now that we've chosen the vector potential and the scalar potential to be time independent, we see that the whole Hamiltonian is time independent. And from quantum mechanics, you know well what to do to find the solutions there. We look at the the homogeneous solutions. So we look for solutions of the form, the static ones, where I just have the phase oscillating with energy E. So I get the time-independent Schrödinger equation with energy eigenvalue E. And we're interested in non-relativistic solutions. So that means we want to look for solutions that have an energy. Well, what should it be? Well, note these particles, they include the rest energy in their Hamiltonian. So they will have energy mc squared plus something small, plus a non-relativistic energy. And this non-relativistic energy, we will assume it to be much smaller than mc squared. Okay, so let's see what these solutions approximately look like. And a convenient thing to do is to decompose the Dirac spinor in a pair of two vectors. So we decompose psi of r to like an upper component psi u and a lower component psi d, up and down, and use that these alpha and beta matrices, they have a nice block diagonal form. So remember, beta was given like this, and alpha the Pauli matrices. So let me write down. So let's take now this equation here with our explicit Hamiltonian and write it out for the two different components. So for the first component, we get the alpha, okay, that becomes a sigma, times, so since it's a off diagonal block, times the down part, the matrix of the spinor. Then we get this part, so q phi plus mc squared times psi u, because now we pick up the plus sign for the beta matrix. And this should be equal to mc squared plus the non-relativistic energy. And then similarly for the other equation, we get the off-diagonal term. Now we pick up the minus sign from the beta matrix. The energy times psi d. And what we notice is, the first thing we notice is that in this top equation, the rest mass cancels. And the other thing we notice is that, well, this part is much smaller than the rest energy. And this part as well. So the potential energy of the electric field, is also assumed to be much smaller than mc squared. Okay. Now this is nice because we can easily solve the second equation for the down component and plug it into the top equation. And we only take into account the rest mass here. So that means that the solution we get for the down component is just dividing by, okay, we have a 2mc squared, we divide by that. So we get a 1 over 2mc times psi u. And this we can substitute in, okay, so in the first term of the first equation. Okay, so now a couple minute calculation comes. I think we can best postpone this to next week, given that we're out of time, and really see where this interaction of the magnetic dipole moment with the magnetic field comes from.